lecture today picks up where the last one left off, right? In fact, this is the second part in a two-part series of us trying to figure out, given certain information, how do we determine either the rate law or the mechanism, or sometimes both? And to give you guys a little bit of experience in doing so. So today we're going to solve 3 examples. And the first example says that the rate law for the hydrogenation of ethylene to ethane over a cobalt molybdenum catalyst is minus Re prime is equal to K times the pressure of ethylene times the pressure of hydrogen over 1 plus KEPE. Suggest a mechanism and the rate determining step that is consistent with the above rate law, and prove that you're correct by deriving the rate law from your suggested mechanism. So when I look at problems like this, and I'm given the rate law and I want to figure out what the mechanism is, I start off by trying to determine what I can ascertain from the rate law itself. And we haven't actually spoken about it this way before. So let's do that here. So we're looking at this rate law. We know that we have some reaction of ethylene to ethane, and that hydrogenation is, right, C2H4 plus H2 gives us C2H6, right? Or, E plus H goes to A, right? And if we're going to look at the rate law, what are we going to be able to figure out? Well, the first thing that I know just from looking at the rate law is the only reactant on the surface is E, right? The only thing that gets absorbed is ethylene. And why do I know that? Well, I know it because at some point in our mechanism, we get something that is like the total number of sites is equal to CV plus the concentration of all the adsorbed stuff. Well, if we look at the denominator here, there's only one thing, right? And that's E. So just by looking here at the mechanism or at the denominator in this rate law, I know that the only reactant on the surface is E. The other thing that I know is that we only have one reaction site. Or how about we only need one surface site? That might be a better way to say it. And the reason that I know that as well is that in the mechanism, we know that we're going to have things like CV, right? The number of vacant sites, and it's raised to the first power. We also don't see too much activity here in the numerator. So we know from the rate law, we only have one active site. The other thing that we are going to be able to know from this is also that adsorption is not the rate determining step. And you might think, how in the world do you know that from just looking at the rate law? Well, I know that because if we only have one site and we are adsorbing the ethylene, if adsorption was the rate determining step, we would have something like, E plus a site goes to E dot S. And so then the only thing that would be in the numerator would be the pressure of ethylene. You wouldn't have hydrogen there because hydrogen doesn't take part in the adsorption step. And so just from looking at this rate law, I know that those 3 things have to be true, that the only reactant on the surface is ethylene, you only have one surface site, and adsorption cannot be the rate determining step because we have hydrogen here, okay? So what would the mechanism look like if this were true? So let's write this. Well, again, E plus H goes to A. And so the first step in this process then has to be the adsorption of E, because we know that that's on that it has to exist on the surface. So E plus an S gives us E dot S. And then we have E dot S plus the hydrogen, right? Because we're going to have the surface reaction. And remember, hydrogen does not adsorb on the surface. Well, A also doesn't adsorb on the surface. So we just have A plus S. And so this is my proposed reaction mechanism based on the information that we're given. And then of course, the second step here is the rate determining step. So if that's the case, right, our rate of reaction is then, and this is K1, right? And this is K2. So if we look at this, our rate of reaction then is simply going to be equal to minus K2 times the concentration of E on the surface times the pressure of hydrogen. And just like we've done in our previous lectures, now our task is to find what the concentration of ethylene on the surface is going to be. And so to do that, right, we're going to take advantage of what we know here about reaction 1. And we know from reaction 1, well, if we said the rate of 1 over K1 is approximately equal to 0. And so from there, we know that that's just equal to, or R1 over K1 is just the pressure of ethylene times the number of vacant sites plus CE dot S divided by the equilibrium constant for that reaction, which I called K capital E here. So then we can solve for the concentration of E dot S, and that's simply equal to KE times CV times the pressure of ethylene. And if we substitute that into our rate law, we have RE prime equals minus K2 times the pressure of hydrogen, then times CE dot S. And of course, then that's just equal to KE times PE times the number of vacant sites. And I'm going to clean this up just a little bit and call that minus K2 times KE times CV times pH times PE. I didn't really make any substitutions there. I just moved the pressure terms so they were together. All right. And now we can find CV. And we know that the total number of sites is equal to the number of vacant sites plus the number of sites that ethylene is on or that are occupied by ethylene. And we know that CT equals CV plus KE times CV times PE, or the total number of sites equals CV times 1 plus KE times PE, or finally, that CV is just equal to CT over 1 plus KE times PE. So let's make that substitution into our rate law, right, where we're going to plug CV in there. And if we do that, this ends up being RE prime equals minus K2 times KE times the total number of sites times pH PE divided by 1 plus KE times PE. And all we're going to do here is call this K. We'll call that just the reaction rate constant. And if we do that, RE prime equals minus K times the pressure of hydrogen times the pressure of ethylene over 1 plus KE times the pressure of ethylene, right? And there's our rate law from our mechanism. And if we want to, let's go back to our example statement here, and that's exactly what the rate law was. So what we tried to do here in this very first example was to look at the rate law and try to figure out what we know about the reaction from the rate law. And then we proposed a mechanism, and then we went through the math to show that our mechanism is correct. Okay, so before we move on, does anybody have any questions about this particular example?
Could you maybe detail one more time how you wrote that second, the rate determining step reaction?
Yes. So you mean how I actually developed that as an equation?
It just looks a little different than some of the other ones we've written.
Yeah, that's a really good question. So when I wrote this first step, right, E plus S goes to E dot S, right? This one here, that's the only adsorption step that we are going to have, right? It's the only species that exists on the surface. So once you form the surface species, it's going to be able to react with the other reactant, which is probably just present in the gas phase, or it's busy sorbed, right? Where it doesn't strongly adsorb on the surface, so it doesn't occupy any sites. So my next step then was to say this intermediate is going to react with the other reactant, right? Hydrogen. And now you're going to get products. Now in some reactions, right, you could end up with A.S, for example. Right, where you then have an adsorbed product. But we don't have that in this case. That we know from the rate law itself, because the only thing here in the denominator is ethylene, that the product that we form is going to be A, or is going to be whatever the products are. And in this case, that's just ethane. And if we're going to just get ethane after this reaction happens and it's not adsorbed on the surface, we have to get the site back. And so that was my logic in writing the second step that way. And you're totally right. It looks a little bit different than some of the other things that we've done before. So does that help? Does that make it a little bit more clear why I got there?
So it's from the denominator that you can tell, okay, that makes more sense. Thank you.
Yeah, exactly. And we're going to use that even in the next example. The denominator, believe it or not, actually gives you a whole bunch of information. Great question. All right. Anybody else have a question that they want to ask? Okay, that was a good one. So let's look at example 2. Now, one of the things that I've been able to do so far when we're solving problems is to do the sort of food network thing where I already know the answer beforehand, right? I already put the lasagna in the oven for 45 minutes. I pulled it out. It's brown and bubbly and delicious, right? That doesn't always happen. And it doesn't always happen even when you've been doing this for a long time. So in this example, I want to walk you through maybe the thought process for an example problem that's not so straightforward. And it's something that it actually took 3 different attempts to show that I was able to develop the correct mechanism or not. And this problem is inspired by problem 5-14. Which we've taken a look at in the homework this semester. And we're given this rate law where butanol is dehydrated to give you 2-butene on the surface of the catalyst. And so we're going to think about it this way as butene is going to go to, butanol is going to go to butene plus water. Okay, and that reaction there is balanced. And again, we have this rate law, right? They just gave it to us in the problem, and then they end up using it, I believe, in example 10-2. And they give you the rate law without any explanation for where it came from. So what we're going to try to do here is we're going to try to figure out where in the world this mechanism comes from. So I'm going to go back to notability, and I'm going to rewrite this, and then we're going to think about this for just a second, because it has something that we haven't seen before. So we have the rate of butene is then equal to K times the pressure of butene over 1 plus K BU times the pressure of BU squared. Okay. So following what we did in the last example problem, can someone come in and tell me at least one thing that we know about the reaction? Just given what's in the denominator here?
Only butanol is on the surface.
Great. Yep. Only butanol is on the surface. Good. Okay. So then in looking in this rate law, what is the weird thing that we've never seen before? And we're also kind of looking at the denominator. What is unusual about this compared to what we've seen before?
How it's all squared.
It's squared. We've never seen that before. Now, where does the denominator come from in our problems?
Usually the CV expression.
Exactly. So if it's squared, what do we know?
Does that mean there's two active sites?
That exactly. So we know there has to be two active sites in the mechanism. Great. All right, perfect. So right now, we know that only butanol is on the surface. We have two active sites in the mechanism to get us to CV squared, okay? And that's kind of all we know from this, from the rate law. Perhaps the other thing that we can take from this, just like in the previous problem, is that adsorption I guess I'm trying to think about this for a second, was that, can adsorption be the rate determining step? And maybe it can. So we're not going to get rid of that first. Okay. So these are the two things that we know about the mechanism. Okay. So let's propose a reaction mechanism. Okay. And we know that there are two active sites, and we've seen examples previous in this semester. For example, oxygen, when it adsorbs in a bridge state on platinum, we saw that you might occupy two different sites. So let's say that butanol reacts with two surface sites, and that gives us this adsorbed species that we're going to call, Bu.2s. And this is just one thing, right? This isn't two different things on the surface. It's almost like a bridge configuration like we saw with oxygen. And then this thing is going to react to give us our products, right? Because those are not adsorbed on the surface. So it has to give us that, right? Plus 2s. And we're going to say that that is K2. Okay. The reason I wrote this as the irreversible step is that we're going to assume that that is the rate determining step. Okay. Okay. So let's do that. So we know then, if it's the rate determining step, that the rate of reaction is simply going to be minus K2 times the concentration of Bu.s, right? Or this thing we call Bu.2s, okay? So if that's true, let's find what this is. And we're gonna do that from the step that's not the rate determining step. So if the rate of reaction 1 over K1 is approximately equal to 0, well, we can do this relatively easily, right? This is just the pressure of butanol times the number of vacant sites squared. So we have CV squared. And then that becomes that's minus, and then plus CBU.2s divided by, we'll call that KBU, okay? And we can solve for this, right? CBU.2s then equals K butanol times the pressure of butanol times CV squared. And so we can put this into our rate law, right? So that equals minus K2 times K butanol times the pressure of butanol times CV squared. And if you look at this, you think, oh, we got it. We absolutely have it. But here's kind of where it goes awry. The next step is to evaluate CV, right? And how do we do that? We do that by this total site balance, where we know that CT is equal to the vacant sites plus the number of sites that are occupied by adsorbed species. And we know there's only one adsorbed species here. So that's just CV plus KBU times PBU times CV squared. So what's the problem here? How do we know from this balance that we can't get the right mechanism? Anybody? What have we done every other time?
What is it when we factor the CV out, there would still be a CV in the denominator?
Exactly.
The rate law?
Yeah, exactly. And so we don't see that here, right? We don't see some strange multiplier here. So this can't be correct. And we know that from here because putting what you said in as an equation, right? That would become CV plus KBU PBU times CV. And nope, that can't happen. So from there, we know that the mechanism is not correct that we've proposed. So this one's wrong. Okay. And, don't be disheartened. In fact, most of the time, the first mechanism that we put out there is wrong. Okay. So let's do this again. Again, we need 2 sites. We can only have butanol on the surface. So another way to think about this is that maybe you break a bond when you adsorb butanol. So let's say that you have butanol plus 2 sites gives you some intermediate that's just like 2, we'll call it Bu star dot S, right? We don't know what it is. We're just going to say, look at some intermediate. And that has K1. And then that intermediate is going to react to give us 2-butene plus water plus 2 sites. And again, in this mechanism, right, this would be the rate determining step. Okay. All right, let's see what the rate law would be. Well, our rate law here then would be equal to minus K2 times the concentration of butanol on the surface, right? This intermediate squared. Now, this looks like it might have a little bit more promise because now if we can get the rate law right, that CV will intrinsically be squared. All right, fine. So then let's use what we know from reaction 1 to find our expression here. And we know that the rate of reaction 1 over K1 is approximately equal to 0 because it's not the rate determining step. And that is just equal to the pressure of butanol times CV squared. That's minus, then plus the concentration of this intermediate squared divided by KBU, okay? And now if we solve this, right, then the concentration of this intermediate squared equals KBU PBU, times CV squared. And that CBU S is equal to CV times the square root of KBU times PBU, okay? And if we plug that in here, right, we're gonna get that R BU prime is equal to minus K2 times CBU dot S squared, which was K2 times PBU times CV squared, okay? And this still looks like it might work because this still has our CV squared, and we have CBU dot S with CV to the first power. So when we do our site balance, right, this is CV plus CV times the square root of KBU times PBU, and CT then equals CV times 1 plus the square root of KBU times PBU, okay? Or CV equals CT over 1 plus the square root of KBU PBU. And I think now you guys can see why this isn't going to work, because we're going to plug this into the rate law, and this is going to equal minus K2 times K2 times CT squared times the pressure of butanol divided by 1 plus the square root of KBU PBU squared. And that's really close, but this square root was not in the original rate law. And so we know then that this also is not the mechanism because it doesn't match. It doesn't match the rate law. All right. Is this okay with everybody? All right. So the next thought here is that both of the mechanisms that we've tried have relied on the active site here, the second active site, participating in the first reaction. We're assuming that butanol is adsorbed in a two-site fashion. So for the third mechanism here, let's lift that assumption and just say, look, maybe butanol is just adsorbed on one site, right? And we get just an adsorbed butanol with a rate constant K1. Well, we know that we have two products. They're not adsorbed, but that doesn't necessarily mean that another site doesn't facilitate the breaking of whatever bond it is inside of the reaction mechanism. So we can have this adsorbed species need a second site in order for that bond break to happen and get our two products that are perhaps only fizzy-sorbed, right? And then we're going to get two sites back. And again, we're going to assume then that the second step is the rate determining step, right? And just like I said, right, these are very weakly adsorbed. So if that were the case, let's have a look at this, that the rate law would be just minus K2 times the pressure, times the concentration of Bu dot S on the surface times the concentration of vacant sites. So then let's figure out what Cbu dot S is equal to then. So then if the rate of reaction 1 over K1 was approximately equal to 0, we're going to get something that looks very, very familiar to us here, right? This is just equal to minus the pressure of butanol times vacant sites plus Cbu dot S over Kbu. And then Cbu dot S just equals Kbu times Pbu times Cv. And so if that's the case now, and we substitute this in, this just becomes minus K2 times Kbu times Pbu times Cv squared, right? Because there's a Cv here and there's a Cv there. And if we do the site balance, right, the total number of sites is the vacant sites plus Cbu dot S. So that's equal to Cv plus Kbu times Pbu times Cv, or Ct equals Cv times 1 plus Kbu times Pbu. Or finally, Cv just equals Ct divided by 1 plus Kbu times Pbu. And so let's plug this in. So R Bu prime is then minus K2 times Kbu times Ct squared times Pbu divided by 1 plus Kbu Pbu squared. And we can call this just K, and we get that the rate law for butanol is minus K times the pressure of butanol divided by 1 plus K butanol times P butanol squared, which is exactly our proposed rate law, or the rate law that we were given, might be a better way to say that, okay? So one of the things that you can see in this example, or hopefully that you see in this example, oftentimes developing a reaction mechanism is an iterative process, even for people who've done this several times. And you very, very often end up going back to the drawing board and thinking about what's happening actually during the reaction and taking a step back and saying, you know, if I want to think about how a reaction like this might happen on a surface, that often influences the rate law. And this is where this idea came from, was that, look, we had, yes, one reactant, but we have two products. And so it's entirely plausible that, you know, you would have butanol, right? And at some point you might have to break a bond. And this part of the molecule goes on site number 1. This part of the molecule goes on site number 2, right? It takes a proton quickly and leaves. This thing doesn't absorb strongly and it leaves. And that's where ideas like that come from as you start to develop reaction mechanisms and you learn a little bit more about how reactions happen, not just that reactions happen. Okay. So does anybody have questions about either the second or third proposed mechanisms, or how the third mechanism is consistent with what was proposed as the rate law? Okay. So if that's the case, let's move on to our third and final example today. And this one has a little bit of experimental data to go with it. So the question here asks us to consider the reaction of Me goes to DME plus W. And for this reaction, we know that Me and W are molecularly adsorbed onto the surface, while DME is not, right? So we know at least this time we have two species on the surface. We also know that the surface reaction is the rate determining step, okay? So the first thing we're going to do is take these two pieces of information and write a mechanism. Then we're going to derive the rate law. And then we're going to determine of the plots here on the right-hand side, which one is consistent with the rate law that we derive, okay, and the mechanism that we have. So let's do that. All right, so we know 2Me goes to DME plus W, okay? Now, again, from the rate law, or sorry, not from the rate law, we're going to find the rate law. From the problem, we know that DME is not adsorbed on the surface, right? And we know that the surface reaction is the rate determining step, okay? So then if we know that Me has to be adsorbed on the surface, that's going to be, and it's the only reactant, that's going to be the first step in the mechanism. So we know that Me plus a surface site gives us Me dot S, okay? K1. And we also know from the reaction stoichiometry here that this step has to occur twice. And that might make you think, well, then why didn't I just write this? And I didn't do that because it's going to make us want to write sort of an awkward mechanism here, that we're going to want to write that the rate of reaction 1 has all these squares in it that it doesn't have naturally. Now, it turns out, because this isn't the rate determining step, all the squares would go away anyway. But when this is the case, I definitely prefer, I'll just acknowledge that, look, this is a single adsorption step. It's got to happen twice, okay? So if we then have 2 of these adsorbed species, what happens in the reaction step? Well, we know then that is going to be transformed into our products. And of course, our first product is DME. But we know then that the second product, W, is adsorbed. And then to have a balanced reaction, right, we have two sites here. We know that we have to get a site back, right? And that's K2. And then the last step in the mechanism is to get our final product off of the surface. So we know then that this is just W dot plus S. And if we were to actually add all of these steps together, right? So we know that we have 2me from here, right? Because of the stoichiometry, we have two sites, right? That's going to cancel with those two sites. We have two of these, we have one of these, right? So our total reaction mechanism is still 2me goes to DME plus W, okay? And I always like to check that to make sure I didn't do anything strange. So now we have a mechanism, right? So this was the first part of the problem. Based on the two things that we know, write a mechanism. And then the second part was to determine the rate law for this reaction, knowing that reaction 2 here is the rate determining step, and we know that it's irreversible. So very simply, right, the rate of reaction is equal to minus K2 times the concentration of Me on the surface squared, right? And so then let's find this. Let's find what this concentration is going to be. And of course, to do that, we're going to use reaction 1. So reaction 1 over K1, which is approximately equal to 0, equals the concentration, or I guess these are gas phase reactants. So we'll actually use the pressure again of Me times CV, then plus the surface concentration of Me divided by the rate constant. So we'll call that K1. And so we find that the surface concentration of Me is just equal to K1 times the pressure of Me, or the partial pressure of Me times CV. We also know later we're going to have to do a site balance, and we know that W is going to be on the surface as well, and we know that that's going to come from reaction 3. So I'm going to do this ahead of time, even though we don't necessarily need it right at the second, okay? And so that is just equal to the concentration of W on the surface plus the pressure of W times the concentration of vacant sites divided by the reaction rate constant. And so CW on the surface is just PW times CV over K3, okay? So now we have expressions for the surface concentration of Me and W, right? The things that are adsorbed. So then let's substitute into here, okay? And when we do that, right, RME prime equals minus K2 times, right, K1 squared times PME squared times the concentration, sorry, CV squared. And I made that mistake here. We've never called it PV before. I just got into this weird mode with considering the pressure of the reactant because it's a gas phase reaction. So sorry about that little mistake, but everything else here is fine. And so now the unknown that's left to solve for is just CV. And we'll do the same thing that we've done, right? It's just the site balance. And we'll plug in the expressions that we derived. So this is K1 PME times CV plus PW times CV over K3. And so CT is just CV times 1 plus K1 PME plus PW over K3. All right. So then our rate law just then equals minus K2, oops, wrong K, minus K2 times K1 squared times CT squared, right? Because CV is just then CT over 1 plus K1 PME plus PW over K3 times CT squared times PME squared divided by 1 plus K1 PME plus PW over K3 squared. Okay. And the last thing that I'm going to do here, again, is I'm just going to combine these and call those K. And R ME prime equals minus K times the pressure of ME squared divided by 1 plus K1 times PME plus PW over K3 squared. Okay. And there's our rate law from our proposed mechanism. And we got there essentially using the same steps that we've used for all of the other problems that we've solved so far this semester. Does anybody have any questions about how we got to here before we do the last part of this example? Okay, I don't hear any. Hopefully that's just you guys getting more comfortable with what it is that we're doing. That, you know, if you see, we follow really the same steps, and it's part of that recipe that I gave you guys a couple of lectures ago. And hopefully that's starting to make a little bit of sense, and hopefully that helps you guys as you start working through the homework that's due soon. All right, let's do the last part of this problem, okay? The last part asks us to use these plots to the right and see which ones are consistent with our rate law, okay? So here, let me do this. Let me paste this in so we can look at these side by side, okay? So what we're going to do here is determine which row accurately describes what's going on in this rate law. So the first thing that I saw was that in all of the plots that are here, that, you know, both 1, 2, 3, and 4, everything decreases with the pressure of W. And you do expect that to be the case, right? Because we have PW there in the denominator, right? And it's in the denominator squared. So right off the bat here, we see that all those plots are the same. We are not at all going to be able to use the pressure of water as a distinguishing factor in this problem. So the second thing we're going to have to do then is we're going to look at the rate of the reaction as you change the pressure of DME. So if you look at our rate law, DME doesn't appear in our rate law anywhere. And so what that means is that the rate shouldn't depend on the pressure of DME. And that's accurately reflected in rows 2, 3, and 4, but not in row 1, right? That shows a decline with DME. So we know then that that row is not the solution to this problem, okay? So finally, that means that we have to look at the response with respect to the pressure of ME. And there's two ways to do this. I'll do this a little bit more thoroughly, and then we'll just maybe just talk about the shortcut really quickly. So we have to do what we did a little bit earlier on, maybe 2 lectures ago, where we started to break down the rate law a little bit. So what would happen to our rate law at low pressures of ME? Well, what would happen then is that at the very beginning, right, PW is equal to 0. And so this would go away, right? And at low PME, what happens is that 1 is much greater than K1 times PME. So then our rate law at low pressures of ME is kind of just minus K times PME squared divided by 1 squared, or just divided by 1. And so we have like a quadratic dependence for how our material, or how our reaction, will respond with the pressure of ME. And because we know that it's quadratic, well, then we actually know that 3 is not going to work, right? Because it showed a linear dependence here. right? So 3 is not going to work. All right, so now we've said that 1 won't work, that 3 won't work. So what is the distinguishing factor here between 2 and 4? And the distinguishing factor is that 1 predicts that as you increase the pressure of ME, that the concentration will go down. The other one predicts that as you increase the pressure of ME, that it will level off. All right, so let's see what's going to happen to this expression at high PME. Okay, and what's going to happen there is, again, that's going to be kind of like 0 at the beginning, and we get something that is like this. But we know that at high PME, that K1 times PME is going to be greater than 1, and so our rate law becomes approximately equal to minus K times PME squared over K1 times PME squared, right? And these cancel. And so that says at high PME, this should be approximately equal to a constant. And so then because of that, we know that 2 cannot be true. And so our answer here, after we've ruled all of those out, is 4. That is the only row of plots that is consistent with the mechanism that we were told after we derived the rate law. Now, I promised I would give you also a shortcut way that you could have thought about this problem. And that is actually, quite frankly, very, very simple, I think. That in lecture 18, we came up with expressions or that described what should happen when we had surface adsorption, surface desorption, and surface reaction limited processes as you change the concentration or pressure of the reactant. And we said in lecture 18 that when you were adsorption limited, that the rate law over the pressure or concentration would be linear. And when we were reaction limited, that it would somehow go up and then level off. And then we were told if we were desorption limited, that it would be flat. And so that was one shortcut way to look at this problem, is to say, well, we know it's reaction limited only after we had ruled this one out at the very beginning because of its false dependence on the pressure of DME. You could say, well, only one of them leveled off, and that's that one. So that's another shortcut way to do this, but it doesn't, give the level of understanding maybe that we had from actually working out the math here. Okay, so as we said, right, from our problem, there's the answer.